For decades, the Toyota Tundra earned its reputation on one simple promise: unbreakable reliability. Owners believed a Tundra could rack up hundreds of thousands of miles with nothing more than routine maintenance. That trust was forged during the V8 era, when simplicity's conservative engineering and massive safety margins defined Toyota's approach. But when Toyota introduced the twin-turbo V6 for the third-generation Tundra, that promise was tested like never before. Reports of engine failures, abnormal bearing wear, oil starvation concerns, turbo-related issues, and inconsistent long-term durability began to surface. Problems longtime Toyota owners were not accustomed to hearing about. Online forums lit up. Dealership service departments noticed repeat patterns. Independent mechanics started seeing similar failures. Almost overnight, the conversation shifted from how long will a Tundra last to what went wrong with Toyota's new V6. Now, Toyota claims the 2027 model year represents a turning point, according to internal engineering updates, supplier revisions, and new calibration strategies. The company believes it has finally addressed the root causes behind the Tundra V6's early failures. So what actually failed? Why did it happen? And is the 2027 V6 truly the fix Toyota needed? Let's break it all down. Toyota's move from the legendary 5.7-liter naturally aspirated V8 to a smaller twin-turbo V6 wasn't really about performance. On paper, the new engine made more torque, accelerated faster, and complied with increasingly strict emissions regulations. But under the hood, Toyota's engineering philosophy changed completely. The old V8 was simple, overbuilt, and the new V6 is compact, boosted, hotter running, and far more complex. According to former Toyota powertrain consultants, the company underestimated how dramatically American truck usage differs from global durability test cycles. Heavy towing at highway speeds, long idle periods, extreme heat, and aggressive stop-and-go driving exposed weaknesses that never appeared in controlled lab testing. That gap between test conditions and real-world abuse is where the problems began. Despite online speculation, most early Tundra V6 failures were not random. They followed several consistent mechanical patterns. Independent engine teardowns revealed abnormal bearing wear much earlier than expected, especially under sustained load. Failures didn't always start catastrophically. Often they began with subtle oil pressure loss, metallic noisy or vibration that worsened over time. Engine builders point to tight bearing tolerances combined with higher thermal loads as a major contributor. Under heavy towing, oil viscosity breaks down faster, reducing the protective film between bearing surfaces. Simply put, the engine was operating too close to the edge. Turbocharged engines place enormous demands on oil systems, and the Tundra V6 was no exception under high RPM and long duration boost. Oil aeration became an issue, especially when oil temperatures exceeded optimal ranges. Once aeration occurs, oil pressure can appear normal while actual lubrication quality drops. That's a worst-case scenario for bearings. Several Toyota master technicians later acknowledged that early oil control strategies prioritized efficiency over thermal stability. Twin turbos generate intense localized heat. In early production engines, heat soak after shutdown became a recurring concern. In extreme cases, especially on trucks used frequently for towing oil coking, was observed in turbo oil feed lines when engines were shut down immediately after hard use. This didn't affect every truck, but when it did, the repair costs were significant. Toyota initially tuned the V6 to maximize fuel efficiency and emissions compliance. That meant aggressive low RPM torque delivery and frequent boost engagement. Calibration engineers familiar with the platform later noted that this placed higher continuous stress on rotating components than originally modeled. The engine made impressive torque, but it paid the price internally. This is where the story becomes uncomfortable. Toyota did conduct extensive durability testing, but those tests are based on standardized cycles, not real owner behavior. Engineers assumed most buyers would use the Tundra as a commuter truck with occasional towing. Instead, many owners used it as a full-time workhorse, directly replacing the old V8. One retired Toyota reliability engineer summarized it bluntly: the engine met the test criteria. The test criteria didn't match reality. That mismatch delayed meaningful changes. Before Toyota ever publicly acknowledged an issue, subtle revisions began appearing behind the scenes. Dealership technicians noted updated bearing materials, revised oil pump part numbers, and quiet ECU calibration changes. None of these were marketed as fixes, but together they reduced failure rates. Still, Toyota knew incremental changes weren't enough. The 2027 update needed to be comprehensive. Internally, Toyota refers to the 2027 update as a durability reset, not a full redesign. The engine architecture remains the same, but the details matter. Toyota revised bearing coatings to better handle higher thermal loads and longer oil intervals. The new materials tolerate thinner oil films without metal-to-metal contact, directly addressing early wear issues. Engine builders familiar with the updated components say this change alone dramatically improves long-term durability under towing stress. The 2027 V6 uses a recalibrated oil pump control strategy that prioritizes pressure stability over marginal fuel economy gains. Under high load, oil pressure ramps faster and remains elevated longer. The efficiency penalty is minimal, but the improvement in lubrication safety margins is substantial. Toyota finally chose durability over decimals on the MPG sticker. Oil flow paths to critical components were revised to reduce aeration risk. Internal baffling changes helped maintain consistent oil supply during hard acceleration, braking, and uphill towing. Experts note these updates closely resemble what aftermarket builders were already doing to bulletproof early engines. Heat shielding, oil feed routing, and cool-down logic were revised. The engine management system now actively reduces thermal stress after heavy use instead of shutting down abruptly. This significantly reduces oil coking risk and extends turbo life. The 2027 calibration spreads torque delivery more evenly across the RPM range. Peak torque is still strong, but it arrives slightly later and more progressively. That small change reduces shock loads on bearings and crank journals without hurting real-world drivability. Independent Toyota specialists are cautiously optimistic. Engine teardown data from early 2027 units shows dramatically improved wear patterns. Oil analysis reports indicate significantly reduced metal content under similar duty cycles compared to earlier engines. One longtime Toyota engine rebuilder put it simply, this is the engine they should have launched in the first place. Failures are never impossible, but the safety margins are finally where they should be. If you're coming from a 5.7-liter V8, expectations matter. The V6 will never be as mechanically simple, but with the 2027 fixes, it finally behaves like a Toyota engine again, durable and designed to survive abuse. For buyers who tow regularly, idle, ostensibly, or plan to keep their truck beyond 200,000 miles, the 2027 update is a meaningful improvement, not a cosmetic refresh. It's Toyota acknowledging reality and correcting course. The Tundra V6 controversies forced Toyota to confront a hard truth. Modern trucks can no longer be designed around ideal usage assumptions. Owners push them harder, longer, and in harsher conditions than ever before. The 2027 fix isn't just about one engine. It represents a return to Toyota's old philosophy engineering for the worst-case scenario, not the average driver. And that's exactly why the 2027 Tundra V6 matters.